All right, welcome back to Lag Demon Programming, and this is a Fundamentals course, but I'm also going to link it in with the Compiler Design course because we're starting to get involved in these things called abstract syntax trees. And I decided to do a short little talk here on what a tree is all about. We're going to talk a little bit about binary trees and different types of trees. We're not going to get into the details of binary trees like red-black trees and self-balancing and so forth, but we're going to talk a little bit about trees and how they work and what they're about. So what we have here, here, data structures again. In this case, we're going to be talking about trees in a very general kind of way. So a binary tree is one that's got nodes in it, and so this is a node, and we're going to call this one our root here, and it's got children, and these children are represented internally by some sort of data structure, usually a pointer, but it doesn't absolutely have to be, that points to another node. And inside here, this is called the parent. That wasn't so good. This is the parent pointer pointing back. Not all trees necessarily have to have a pointer back to their parent. They can. So this has the ability to point back to its parent and to point to its children. Now this is probably called, possibly left and right, these 2 points. Or it could be called something else. It doesn't matter. The general idea, though, is that every node has a parent and 2 children for a binary tree. And that is really why it's a binary tree. It has 2. Left and a right, or a first and a second, or whatever you want to call them for the purposes of your particular binary tree. There are many applications for trees, and there are many applications for binary trees, but the most common one and what is taught the most is the idea of sorting. And that works like this. You've got an empty binary tree container of some time, and you stick in a numerical value, and your node is created, and the root node is created right then with, say, a numerical value of 9 in it. Great. So you now have a binary tree where these the 2 children don't exist. They're null, or they're nil, or whatever you want to call it. But you just have a 9. So then what happens if we go and stick or insert another number in here? Let's say we put in an 8. Well, we have a rule that says that if the number is less than or equal to, we'll say less than the value of the current node, then we're going to push it to the left. So we would come down here and put the 8 in here. Okay? If we then put in 12, it would see that it's greater than 9, so it would push it over here, and it would put in a 12. Now, we're always feeding these numbers into the root. That's what we know about, is the root. And that root can actually change. We can rotate this around in special ways. That's balancing. We're not going to talk about balancing in this discussion. We're just going to talk about the way binary trees work in their most common mode, which is this sorting process. It's kind of an automatic sorting. Let's say that we then put in a 6. Well, it looks at it and it says, okay, well, 6 is less than 9, but I already have a child to my left, so we're going to insert it down to the child on the left, and it says 6 is less than 8, so it comes over here and it creates another node called 6. Okay? And then if we put in, and there's nothing between, we're just working with integers, there's nothing between 8 and 9, so there would never be anything over here. If we were working with decimal numbers, there could be. We'll just stick with integers. So let's say we put in something like 10. So we put in a 10 into here. And this algorithm in here sees this 9, says, well, that's greater than 9. It's got to go to the right, but we've got something to the right, so let's insert it to that, give it to that, and say, hey, insert this. It says, well, 9, so 12, it looks at that, compares it, says, well, 10 is less than 12, so we'll insert it over to here, to the left. And there's our 10. And if we put in a 13, it will end up over here, okay? Now, the way you walk this and get it back into order is you come down here and you start going all the way to the left until you come to something where you can't go any further to the left. And that's your lowest number, which in this case it is, a 6. So we put out a 6. And then there's nothing to the right, so we go back up to here. There's nothing to the right, or back up to here, and we find an 8. And there's nothing to the right here, so we go back up to here and we find a 9. Well, now we got to go to the right. So we go to the right because there is something to the right, and then we go to the left. We're going all the way down. As long as we can go to the left, we go to the left. And the next number we get is a 10. And then we come back to the 12, and it's got something to the right, so it's got a 13. And there's all our numbers came out in order by following that algorithm. So it's always move to the left when you can, and then if you find a number furthest to the left, then that's your next number. If you can go to the right, you have to go to the right. So if we were to now put a 7 in here, inject it in, 7 is less than 9, 7 is less than 8, this 8 would come in here and insert a 7 in here. If we were then to walk this tree to find it, we would say, okay, well, we can go to the left, we can go to the left, we can go to the left. So we got a 6. We can't go any further. There's nothing to go to the left anymore. Then we got to try to go to the right. We can't, so we go back to the 8. But when we get back to the 8, we can go to the, oh, wait a minute. I put a 7 in there. That's incorrect. I put that in the wrong place. I'm sorry. 7 is less than 8. But it's greater than 6. So the 7 would end up over here. We're getting a little bit unbalanced. Would end up on this one. Because it would come down, it would try to insert it here, and 6 would go, well, that's greater than me, so it's got to go over here. So we come all the way down to the left as far as we can go, and we get a 6. And we find that. Then we've got to go to the right, and we find a 7. And then we come back to the 6. We've already done it, so we go back to the 8. And so forth. And otherwise, after that, it's the same pattern, 9, 10. I missed a 12 up here, I guess. 12, and then 13, by following that pattern. That's, in general, how binary trees work. In our compiler design course, and this is why I brought up the idea of trees and walking through trees, is we're going to be working with a different kind of tree. It's a little looser than what we think of in terms of, I don't know why that sticks around after I erase. It's a little bit looser than that binary tree. Our tree nodes, some of them don't have any children at all, like a value node. So a value node will always end up being a leaf. Because it doesn't have any children. But if we think of something like an expression node, an expression node is very similar to a binary tree in that it has a left and a right, and it contains within it some sort of operator. I'll put it over here. We'll put a general operator symbol. It has some sort of operator associated with that, and that can have other expressions under it. But our overall tree, this expression could be part of something else. For instance, this could have an expression here, and it could, if this is a binary operation, then it has to have two expressions, one on the left and one on the right. And that expression could ultimately be a value. It could be a value here, and it could be a further expression here, and so forth. And we organize according to this tree. Other kinds of expressions we might have might be an if, then, else expression. Let's do that, if then else. And an if then else has to have a condition, which is an expression, but it's usually a Boolean expression with a Boolean value to it. It has a then expression, something that if this is true, so this would be the true expression. And it has an else part, which has a false expression, or in other words, an expression we're going to return if this condition is false. That's how a trinary expression might work out, or an if then else. We also have possibly statements that don't return a value. And so those statements might have a whole variety of children under them for different parts of the statement, for different aspects of them, parameters and so forth, might be individual nodes that it needs to know about. So a tree of this nature, and I'm going to erase this and make this a little bit more clear. What we call this is an abstract syntax tree. It's still a type of tree, but it starts becoming a representation of our computer program. So we can have a series of nodes in a list that represent each group of some kind, whether it be perhaps it's a function or a let statement. If it's a functional program, these individual ones in this list, and it might be a linked list. It probably will be some kind of a linked list, or what we call a vector, which behaves more like an array. But each one of these would be some function in our program, and that function would contain stuff. It would contain expressions and parameters and so forth. And those parameters have types. I'm not writing this very well. These parameters have types, and they have names, identifiers. Okay, and so our program starts getting broken down into this tree with different kinds of things in it, so that we can break it down into how its program operates and works. And that's what we're doing with the abstract syntax tree, is building this tree of objects out based on the compilation of our program, based on its syntax, based on the way it parses. It parses into this abstract syntax tree. So some ideas about how that could work, you might have, a real common thing is this for loop. We've seen that in many programs. How would a for loop break down? Well, a for loop typically has some sort of a start value or an initial value. It has some sort of end value or condition to end, okay, and some way to perhaps increment a value or adjust or change. We'll call it modifier. This is the modifier part. So each of those would have to be some sort of an expression node. These are the expression nodes of it. So this is the for node, and the for node has as children each of these so that it knows about them. And then some of these could be expressions, like this condition could be an expression with a whole tree underneath it of expressions and additions and or different kinds of stuff that come up with that condition. The same with the start and the end, or this modifier rather. This modifier here could be any kind of an expression that modifies how this loop behaves. And all that has to be stored as objects connected together underneath this tree. So that's kind of in general, and we're going to continue on with the code in it in the compiler design course. And a link to that compiler design course will, of course, be along with this. I hope you can follow this. I'm not tremendously good at drawing on the screen like this, even though I have a pad and a stylus that I'm using and not a mouse. But I hope that helps clarify it what the different kinds of trees are. We've got binary trees that have nodes like this. And then we have other kinds of trees, especially things like abstract syntax trees that can be quite different. This one might only have one node under it. This one might have 2 or 3 nodes under it, and so forth, depending on what the operation is. Some of them might have 4 nodes under it. It just depends on what each of those operations within the program needs. Then the other thing about that is, and one of the things that's nice, I'm going to erase some of this here, is that there is a pattern that we're going to use, and I'll talk about this in another lecture as I talk about these fundamental things. We're going to use a visitor. And that's a really slick way to code this up so that we can walk through this more complex tree. This tree can kind of be self-walking because it knows it has a left and a right, always has a left and a right. These nodes, we don't necessarily know when we enter a node here abstractly as a node whether or not it has 3 or 7 or 5 or 1 or 2 or none as far as children goes. But the visitor has the ability to process every type of node that we put in this, and what will happen is the visitor will ask this to accept its visitation, and this thing will call back to the visitor a proper function that lets it process each and every one of these nodes. So that's the reason one of the ways we're going to use this abstract syntax tree to accomplish the processing that we need to do with a visitor, which are going to be things like resolving all of our identifiers. We need to IDENT, identifiers. We're going to resolve all our identifiers and determine what they are, map them out. We need to resolve all of our types, and then we may need to do a little cleanup, and we'll use visitors for each one of these. Each one of these will be a different visitor that will walk through the abstract syntax tree. And then finally, we're going to need to emit some sort of code that's executable. And we're going to do that in a couple of different ways probably. We're going to probably have some internal ways of doing that right inside of our engine, and we may have an external way using a JIT compiler of some kind, using some sort of bytecode or intermediate representation of some sort to accomplish that. So that's just a little kind of brief about the idea behind trees. They're similar to linked lists, but they're a little more complex. There's more linkages to more nodes. And one thing I should point out is trees are, by definition, they are graphs. If you're familiar with graph theory, they are graphs. They are directed because you have a direction. You can go from, how to get from this node to this node. There's a direction to it. And they are non-cyclic, which means they don't ever loop. This one doesn't ever point up to here. You can't run down through here and then get directed up to here and go in a loop. That doesn't happen in a tree. A tree is always non-cyclic. So it will always, if you follow any path down, the tree will always end at something. And we call these endpoints, we call them leafs. They're the end of a path within the tree. If it's cyclic in some way, then it ceases to be a tree. If it's got cyclic in it, if it's got loops in it, it is no longer a tree. So that's what it is. It's a directed non-cyclic graph is what a tree is in formal discussion of these things. So that's it for this lecture. I hope you enjoyed it. I hope you got something out of it. I will see you from here, hopefully, back in the compiler design course, where we're going to be starting to work very heavily with our abstract syntax tree and building things up and working with our visitors and so forth to accomplish various things that we need to do for our compiler. So thanks for watching. I hope you enjoyed it. If you liked it, hit that like button. If you really liked it, hit that subscribe button. And if you want to get notifications when I upload videos, hit that notify button. And I will see you in the next video. Thanks for watching.